Bam! Mr. True. In this video, we're going to be taking a look at number 5 of the 2017 AP Calculus AB questions. In the description, you'll find timestamps to jump ahead to any of the 4 parts of this question. You're also going to find links to the AP Central website where you can find the PDF of all of these questions. You can download the PDF of the marking schemes of these problems so you can see how the points were awarded for certain parts of your work. You can find PDFs of the Master Scores graders commentary so that you can figure out where students most often lost points or earned them to help you prepare for your AP test. Okay, so we have 2 particles move along the x-axis. For t being greater than or equal to 0 and less than or equal to 8, the position of the particle p at time t is given by x sub p is equal of t is equal to the natural log of t squared minus 2t plus 10, while the velocity of the particle q is given by v sub q of t, which is equal to t squared minus 8t plus 15, where q is at 5 when t is equal to 0. So we have a couple of particles, right? We have some information about p, some information about q, and we have an initial condition for particle q. And remember a few things before we start here. Of course, we have a position function. The derivative of position is velocity. The absolute value of velocity is speed. And then we have the second derivative of the position function is acceleration if it happens to come up. For t, which is greater than or equal to 0 and less than or equal to 8, when is the particle p moving to the left? Or in other words, when is its velocity negative? If your velocity is negative, you're moving to the left or you're moving down. And if your velocity is positive, you're moving to the right or you're moving up. Well, we don't have a function for particle p's velocity. We have a function for particle p's position. So then we're going to say that the velocity, let me get this out of my way here, we have that x prime sub p of t is equal to, and the derivative of a natural log is u prime, that function inside the natural log, over u. So we're looking at 2t minus 2 over t squared minus 2t plus 10. So all we need to do is figure out where is this velocity function, well, negative. Well, if you remember back in pre-calculus, if you want to solve a rational inequality, you find out where the numerator is equal to 0, where the denominator is equal to 0, mark all those points on a number line, and you start just simply checking the number line between those sort of critical values. Let's start with the denominator. Okay, so first thing we want to do is think about, well, where is t squared minus 2t plus 10? You know, where's that equal to 0? If you go to solve that, if you want to try and factor it, it doesn't factor. If you want to try and do the quadratic formula, that's great. It's probably what you should do. If you want to check the discriminant to see if there's even any solutions, you could say, well, your discriminant is equal to what? B squared minus 4ac. So b squared minus 4ac. Well, that discriminant is going to be less than 0, so therefore no solutions. This quadratic does not intersect the x-axis, and this parabola is opening up. Thus, the denominator is never going to be equal to 0, but the denominator is always going to be greater than 0. Now, that's not the only way that you can come up with that answer. You can remember that the domain of t, and this is a good idea to, when you read your AP questions, to highlight all the important information with your pencil. T is only for, these models for velocity are only for when time is between 0 and 8. And you can think about plugging in 0, 1, 2, 3, 4, 5, 6, 7, 8 just quickly in your head, and you'll see that this is always going to give you positive values. But I wanted to review that discriminant use. So the only critical value that we're going to get for x prime, or the derivative of x sub p dt, of t, is to look at the numerator. So we have 2t minus 2 is equal to 0. Again, we're looking for where x prime of the derivative of x sub p of t is equal to 0. that's going to equal or occur when t is equal to 1. Now, I like to analyze the sign of derivatives by looking at a sketch when necessary, or when possible, excuse me, and only do it in the sign tables when necessary. Now, you may have a completely different opinion about this. You may want to think, okay, well, I'm going to check for the interval between 0 and 1 and between 1 and 8 and plug some numbers into this only part of the derivative that's going to change sign. I might look at this and go, well, the denominator is always positive, so forget about that. The numerator is a line whose y-intercept is 2, negative 2, and whose slope is positive 2. So just doesn't have to be exact, but just here is a sketch, if you will, that's going to help me determine where x prime, the derivative of x of p of t, is equal to a negative value. And you can see that this line is below the x-axis to the left of 1, or if you plug in something like 1/2, 2 times 1/2 is 1, minus 2 is going to be a negative value. So the derivative of the velocity, or the velocity of particle p, is less than 0 on that interval, the open interval from 0 to 1. Therefore, the particle p is moving left, and really we could say that that's a closed interval, because, well, when I plug in t is equal to 0, I get a negative answer, and 0 is part of that domain. So particle p is moving left when t is greater than or equal to 0 and less than 1. And that is the end of part 1. No. Part B says, for t which is greater than or equal to 0 and less than or equal to 8, find all times t during which the two particles travel in the same direction. Now, let's make sure that you read this nice and slow, and I said it correctly the first time, and you just don't just jump into, oh, well, they gave me two position functions, right? It actually does say v to kind of help you remember that that's velocity, but the two particles move along the x-axis, and the position of particle p is given by this function, while the velocity of particle q is this function. So actually, we already know this is a velocity function for p, and this is the velocity function for q. And we already know that particle p is going left on 0 to 1 and right on 1 to 8. Now let's analyze q. If you factor this, we're going to have that we have t minus what? 5 and t minus 3. And just to give you the option or the different look, you've got your number line. We've got 0, 8, we have 1, and that is good for particle p, where p is negative here and positive on this interval. And then we've got q. Well, now this is I really like the graphing way of looking at these, but we have a critical number at 0, we have a critical number at 3, and 5, definitely not drawn to scale, and up here at 8. Now, think about something like 1. 1 minus 5 is negative 4. 1 minus 3 is negative 2. Negative times negative is positive. At between 3 and 5, something like 4, you've got 4 minus 5, which is negative, and 4 minus 3, which is positive, and negative times positive is negative. And then we go between 5 and 8, like 6, it's going to come out to be a positive answer again. And you just look at this table, and you identify the areas that have, where the two velocities are giving you the same sign. Well, between 1 and 3, they're both positive, and doesn't look like there's any time interval 0 to 1, 1 to 3, 3 to 5, or 5 to 8 where both velocities are negative, but they're both positive again on this time interval between 5 and 8. So particle P and Q particle P and Q are traveling in the same direction on the time interval of 1 to 3 and 5 to 8. Those are open intervals because at time equals 1, our first velocity is actually 0, while the second velocity is positive. And at 3, our velocity for particle Q is 0, while the velocity for particle P is positive, and so on and so on. So those are open intervals. Just double checking. Almost made a mistake. They're both positive at 8. And it's because the velocity function for P and the velocity function for Q have the same sign. They're actually both positive. We could say they're both positive or they're both moving to the right, but the question said when are they moving in the same direction? Now, you might love this. I think it works mentally for me very well to look at it this way. We have just the numerator of the velocity function for P determining its sign. So we have that that derivative function has a y-intercept of -2 and a slope of +2. So we have this going on for particle P. I'll put that in purple, which probably isn't going to show up on the camera. And then we have the discussion here that this velocity function is a quadratic opening up and has an x-intercept of 3 and 5. And it's a parabola opening up. Each of these zeros have multiplicities of 1, meaning that the derivative is going to cross through the x-axis. And between 0 and 1, this velocity is negative, or this velocity is positive. Between 1 and 3, both velocity functions are given as positive answers. Between 3 and 5, this velocity function is positive, this velocity function is negative, and between 1, 2, 3, 4, 5, and 8, both velocities are positive. That's just the way I like to see it. So I do a lot of times sketches to analyze the signs of my derivatives or second derivatives as opposed to a sign table, but whatever works for you. Make sure you write your final answer in context of the problem with specific time periods and explaining exactly what is going on. Part C coming up right now. Find the acceleration of particle Q at t equals 2, and is the speed of Q increasing, decreasing, or neither? Okay, well, first of all, it would have been nice if I had left the velocity of Q up here. The velocity of Q. Okay, they just want to make sure that you know when is speed increasing. Speed is the absolute value of velocity, and when the velocity and speed have the same, no, let's try that again. When velocity and acceleration have the same sign, whether they're both positive or both negative, they don't have to be both positive. A lot of students think that incorrectly. If the velocity and acceleration have the same sign, then the speed is increasing. So we have the velocity function, yeah, t squared minus 8t plus 15. So v prime sub q of t, which is the acceleration of q. I'm going to go ahead and link these together so I can just say acceleration and velocity. But make sure you link these together. Do not just take a derivative and write a sub q is equal to t. They want to see that you understand that you have taken the derivative, not just made up some new random function. That's 2t minus 8. Find the acceleration of the particle at time t. Well, you really need the velocity as well. So I'm not going to run out of room. V sub q of 2 squared minus 8 times 2 plus 15. So we have negative 16 plus 15 is negative 1 plus 4 is equal to 3. And there's not an application problem here, but it is velocity. So it's like 3, well, it's just 3. It'd be 3 units per some period, specific time period. And then the acceleration at q, so a sub q of 2 is 2 times 2 minus 8. 4 minus 8 is equal to negative 4. I'm sure that this can't possibly be anything wrong with this. No. Okay, so v q of 2 does not have the same sign of a of q. Therefore, the speed v sub q of 2 does not have the same sign as the acceleration, or a sub q of 2. Therefore, the speed of the particle of q at specifically time equals 2 is decreasing. Okay. You could also say that the velocity and acceleration have opposite signs, again, specifically at that particular time period. Let's get on to part 4 right now. Part D, find the position of particle Q the first time it changes direction. If you've made it this far, thank you so much. And if you would please do me a favor, hit that like button to help the YouTube algorithm. I would really appreciate it, as well as sharing with any friends that would listen to you. Find the position of the particle Q the first time it changes direction. I just said that, where x is equal to 5 and t is equal to 0. Remember that initial condition that I've now erased the problem, but I kind of boxed in and started highlighting all that information they're giving us. Also, in a previous part, we looked at that velocity function for particle q. We factored it and set it equal to 0. I made a sign table, but I also talked about this being a parabola that opens up. And here's this little sketch that maybe I would have in my work. Hopefully, if you like this, you will too. Because now I can just glance at this and go, well, you could glance at the sign table as well, and say, well, the first time that the velocity changes sign is at the x value of 3. Well, okay, boom. That's what we're looking for. We're looking for the position of particle q. I'm going to write this out because we don't have a function name, basically. I could basically define one, but I don't have a function name given for position. So position of particle q at t is equal to 3. Is equal to, I'm going to just glance at this. Yeah, I could do this. There. I just like to work with math notation. It turns out they did as well. So x for position, linking it together. So I'm not kind of defining my variable now. Is equal to, well, when you integrate a rate of change, you get an amount of change. An amount of change from where? The amount of change from the initial position of 5 at t equals 0. So the position of particle q at 3 is equal to the position of particle q at 0, and then off of 0, you're going to start integrating that rate of change to get an amount of change off of, well, that initial time period of 0. So the position of particle q at time 3 is equal to the initial position of 5 plus the definite integral from 0 to 3 of that velocity function. So t squared minus 8t plus 15 dt, 5, bad habit, 1/3 t cubed minus 8 divided by 2 is 4. Dividing by 2 because I've got that raised power of 2 now, plus 15t. We're just going to plug in the values of 3 and 0 and do some arithmetic. Now I'm just writing a minus 0 once for us. Then so we plugged in our upper limit. We're going to work out the arithmetic, minus, then plug in the lower limit. When you're plugging in a lower limit, or any limit for that matter, value of 0, don't just default to the whole expression equaling 0. I've had kids do that when there was maybe a cosine function in here and the cosine of 0 is 1. So don't just jump to, oh, the answer is 0 when I plug in 0. And right here, this is not a huge number, but I do like to remind my students to reduce instead of take these powers and make the numbers really big and then try and figure out what you're going to divide by and what it comes out to as you divide. You've got basically 3 cubed divided by 3 to the first. Well, that's going to give you 3 squared and the phone. So we have 45 minus 30, which is 15, and 15 minus 6 is 9, positive 9. Now we have 9 plus 9, which is 18, and 18 plus 5, which is what? 23. So the position of the particle, the first time it changes direction, is 23, and that is specifically, though, when t is equal to 3. I'm Mr. True. That's the end of question 5 from the 2017 Calculus AB exam. I'm Mr. True. Bam! Go do your homework.